Redox reaction is one thing losing electrons and another thing gaining electrons, and that results in a transfer of electrons. And when those electrons flow through a circuit, this is a circle with a break in the circle, which is literally an on and off switch. So when this circle is broken, when the circuit is broken, this is turned off. But when the electrons are allowed to flow, when this switch is closed and this turns on, then you have this electricity that is having the light bulb or a smartphone or anything that is plugged in with the electricity. Now this isn't plugged in, but this is a battery, and the battery is providing energy that's chemical energy, and the chemical energy typically is coming from the two substances, and it's a difference of potential energy between those two substances, that something from higher energy releases its electrons to something naturally flows down to a lower energy, just like potential energy of a waterfall. What's labeled on a battery are these electrodes. So there's always going to be a negative side of a battery and a positive side. Now here they're both on one side, but if you notice an AA battery or a C or a D, the cylinder has one end as a negative end and one end's a positive end. If you've ever put that in without the positive and negative end in the correct direction, it needs to be in a certain direction. That's because on this negative side, these are both called the electrodes. The negative is the anode, and this negative is also similar to anion, is a negative charge ion. And the anode is where the electrons are lost, so they flow out of the negative side. And then the positive side, this is called the cathode, has a positive label, and similar to a positive ion that's a cation, this is where the electrons flow in. So this is where the electrons are gained.
What I have here is an energy stick, which shows how a circuit works. So inside of this energy stick are lights that light up red and green. This is why I'm in this area that's a little bit darker, so you can see the lights. Now, this is not lit up because the circuit is not closed. There are two ends of the circuit that need to be connected through the circle, which is going to be through me. Hold one end of the circuit, you can see that the lights are not open, but the closing the circuit will require me holding onto the other end, and you can see that now these will light up because the circuit is closed. And the second I take my hand off, the circuit's open. So this is an on-off switch, is opening and closing the circuit.
There's a flow of electrons from the anode to the cathode, and that's due to the difference in potential energy between two substances inside of the battery. Inside of the battery are usually metals that are undergoing these redox reactions. So one metal loses electrons and another metal gains electrons. So each metal will lose or gain electrons based on what's called its oxidation state. And this is nothing you have to memorize. It's just something to notice, that it is these oxidation states are related to something we've already learned, which is the charge values. So in family 1A, 2A, and 3A, 1A and 2A and 3A, these form +1, +2, and +3 ions. And in 5A, 6A, and 7A, these form -3, -2, -1 ions. These are the oxidation states. Some metals have more than one possible oxidation state, but this is the process of losing electrons forms a positive charge ion. Losing electrons forming positive charge ions, those are cations, the metals on the left, or gaining electrons, these are nonmetals on the right of the stair-step line and the right of the periodic table, and those form the negative anions when the electrons are gained. Not shown here are individual metals having what are called electrical chemical potential values, and it's that difference in the potential energy values, the electrical chemical potential, that difference drives this flow of electrons. And so the difference between the two metals that are losing and gaining electrons is driven by the potential energy, but the difference is measured in voltage and volts, and that's the output of energy from a battery. I mentioned earlier that the voltage of a battery is not related to its size. All of these batteries, these are all alkaline batteries, these have the same voltage. They're all 1.5 volt. except for this, you have a 9-volt battery that's shown here. And so why they have the same voltage is because all these batteries, different sizes, have the same two substances with that difference in electrical chemical potential. And so the potential energy difference between the two substances is dependent on exactly what type of battery it is. So the standard alkaline batteries, they have the two metals zinc and manganese. And in the electrodes, zinc is oxidized and manganese is reduced. So the sizes don't matter, only the metals. So the 9-volt battery has different metals. A lead acid battery in a car has different metals, as well as rechargeable batteries. This is different batteries have different substances inside of them. The larger sizes just means that there's more chemicals and it can last longer. And so these are not rechargeable batteries. When you also can have more than one battery in series, that will just give you more life because in general you're having more chemicals when you have more batteries. More batteries can also increase the voltage, but not the amps, which is the current and the flow. But these are primary batteries that are not rechargeable, and these will go dead. This, in the process of converting from chemical to electrical energy, the chemicals get used up. Rechargeable batteries, on the other hand, are called secondary batteries that you can run the redox reaction in the reverse. By adding electricity, you can turn the chemical energy back into stored chemical potential energy, and running that in reverse will then recharge the chemical side and then allow this chemical energy to go back in the direction to provide electrical energy. These are some other common batteries, or they're called galvanic cells. And so these are your standard household alkaline batteries. Those were the ones that contain zinc and manganese. But this is also pretty standard, is a lead acid battery in a car. And you can see that this has a higher voltage, 2.1. Higher voltage means there's different metals in there. These are all, what they all have in common is these are all portable sources of energy. So these all are used for things that don't need to be plugged in, like portable electronics, those household batteries, or a car, or your electronics have lithium batteries or lithium ion batteries. And this is the most important, is this lithium ion has the highest voltage overall, 3.6, and that's what you need for the laptop computers. So for the standard household alkaline batteries, there's manganese and there's zinc. So the cathode, the reduction, manganese is gaining electrons. And this is more complex, this half reaction. It's a half reaction because we can see the electrons in there, and you see some ions, but the electrons are still the same idea. If the electrons are on the reactant side, these are electrons gained, and that's the reduction half reaction. This anode, what's going on at the anode, this is the oxidation half reaction. Even though it looks more complex than what we've seen before, as long as you can find the electrons on the product side, on the right side, then you know the electrons are lost, and that's an oxidation. When you put the two half reactions together, you no longer see the electrons anywhere in the balanced equation, and that's the reason why we have the half reactions in the first place, to identify what's going on with the electrons so we know which was oxidized and which was reduced. This also shows an example of the circuit that the electrons flow out of the anode and through the circuit to supply electricity to whatever the device is, and then back in through the cathode. So lithium-ion batteries are an example of the rechargeable batteries that can be recharged, or you can have the redox reaction go in reverse. So this is a secondary battery, and these are first developed in the 1990s. And for being the first portable and rechargeable batteries, the developers of lithium-ion batteries, the scientists behind it, won the Nobel Prize in October 2019. So this allowed for laptops and tablets and iPhones and the future for solar power, for storing a larger amount of energy in these types of batteries that have higher potential energy and are rechargeable. So you could take your electricity generated from solar power and put it into a lithium-ion battery. So this is also showing the two half reactions that are more complex than we've seen before, but we can still figure out that if the electrons are on the product side, that's oxidation half reaction. Electrons are lost, and so that's oxidation is the anode. When you have electrons on the reactant side, on the left side of the arrow, that's going to be the reduction half reaction. Electrons are gained, and that's the cathode. As you might expect, there's an environmental price tag of batteries. The batteries, which are very common in our everyday lives, when you think about it, when is the last day you went an entire day without using a battery-powered device? So even though batteries are relatively inexpensive, batteries are made from metals, and metals have to be mined. And some of these metals are pretty rare. And so not only rare, but they might be endangered, kind of like how animals are endangered. So these are endangered, like zinc and gallium and silver in the next 100 years. Or increased use of these, which are rare metals. They're definitely rare metals down here, and risks to the future supply of things like tin or SB's antimony and bismuth to be, taken from the original source and processed using lots of energy, and often produces toxic waste in the process. So dead batteries themselves are considered chemical hazardous waste, so it's important to specifically recycle your batteries in battery recycling. And this is so that the metals inside can be reused instead of being toxic waste in a landfill. So for electronics to be sustainable, you absolutely must recycle your batteries.